This is Module 6, Lecture Notes 12. Today we're going to dive a little bit deeper into stoichiometry. Okay, I want to take you back to the last problem that we left off last week. We were talking about a real-life example of where we would use stoichiometry. And remember, in this problem, a citric acid manufacturer wanted to manufacture this many moles of citric acid. And they wanted to know how much water they would need in order to do that with their reaction. And we got 70,000 moles of water for our answer. So if somebody told you, hey, go get me 70,000 moles of water, how would you do that? Well, moles are not very easy to measure. You can't put them in a graduated cylinder. You can't place them on a scale and weigh them. We have to relate moles to a quantity that we can actually measure physically. And that is often done by relating it to grams. Okay, so to wrap up our stoichiometry unit, we are going to introduce the concept of switching moles to grams all the way through a reaction. These are going to be 4-step problems. Okay, so for those of you that are like me, if you know me at all, I like organization. I like to know how to begin something, how to end something. You will love these problems because they always step through the exact same way. You will be given a mass in grams to begin with. You will convert that to moles. And then you will use the mole ratio to switch that to moles of another substance. And then finally, you will switch moles back to mass or grams in the end. These problems will always be 4 steps. They will always go in that order. Start with a mass, switch it to moles, use your mole ratio, switch it to mass. Okay, so let's step through one of these together. A chemist needs to make 100 grams of gallium chloride. I always like to write my numbers that I begin with right under my reactants or products in the chemical reaction. I want to make 100 grams of this. The question says, how many grams of gallium do I need to do that? Okay, so we are starting here. We're going to use our mole ratio to figure out how much reactant we need. So your setup would look like this. You always start with what you know over 1, right? That is your first step, your mass. Okay. I don't want grams anymore. Remember, we want to switch it to moles. So I have to put grams of gallium chloride on the bottom so that they'll cancel. Well, what's the mass of 1 mole of gallium chloride? Do you remember how to get that mass number? You need to go to your periodic table and add up 1 gallium and 3 chlorines. So go ahead and do that off to the side. You should get 176.2, and we can just call that 176 when we plug it into the problem. Okay, so we've done this first part. We've started in mass, we've canceled our grams, and now we're here at moles of gallium chloride. We've learned that if I want to switch from moles of one substance to moles of another, that's where I use the mole ratio. For every 2 moles of gallium chloride, using my coefficient, I need 2 moles of gallium. It's a 2-to-2 ratio, using my whole numbers that were out in front. Okay? And my last step will always be to switch my moles back to mass. Okay? So for every 1 mole of gallium, how much does that weigh in grams? Gallium is 69.7 grams. Okay, let's check our units and make sure they cancel. Grams, grams, moles, 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 and I'm left with a mass, and that's what I wanted to find. When you do this in your calculator, I would prefer you to multiply all the way across the top. So you should plug in 100 times 2 times 69.7. Then you're going to divide by 176, press equals, and divide by 2. You should get 39.6 for your final answer. Make sure you label it. This is grams of gallium. These blue calculators, or whatever color your Texas Instruments calculator is, if you have one of these, they are super picky about how you do your denominators. That's why I did it in 2 steps. I told the calculator to divide by 176 and divide by 2. So it knew I wanted both of those on the bottom in my problem. Okay, before we move on to the next problem, let me point out a couple things that I often get asked or that I see students mess up on in these problems. First of all, you will always have 4 steps set up like this whenever you're going from mass to mass. I often have students ask me, how do I know if I put a 1 with the word mole or I put another number with the word mole? Here's the rule. You always use a 1 with a mole, except in the mole ratio step, and that is right here. And if that helps you to label it in the example, then please do that. The reason we don't use a 1 in this step is because these numbers come from the coefficients in our chemical reaction. Sometimes they happen to be a 1, and that's fine. But in the mole ratio, you need to look at your coefficients. These numbers in front of a mole are conversion factors. 1 mole of gallium chloride weighs this many grams. 1 mole of gallium weighs this many grams. That's why I have a 1 here. Okay? I'm going to stop talking. I want you to go ahead and start on the second problem. It follows the exact same 4 steps. So please take your time, work it out, and then check your answer. Let's see how you did. They gave me 100 grams of acetylene to start with. So I'm over here. We know that we need to get rid of mass, so it goes in the bottom. And I found the mass of C2H2 by adding up the elements in the formula. And I got 26.02. I'm just going to use a 26. 26 grams per 1 mole. Make sure you have that. Next is my mole ratio step. And this is very important that you have it correct and you have it in the right order and not flipped. Okay, we are starting here with acetylene, and because it doesn't have a coefficient, it's 1 mole of the C2H2, and I'm trying to figure out how many moles of water. 2 should be on the top. 1, 2. Now I have moles of water. I don't want those anymore. 1 mole of water weighs how many grams? up H2 plus an O, and you should get 18.02. You can use an 18 if you want. Okay, please practice plugging this in properly. 100 times 2 times 18. Then press equals and divide by 26. You should get 138.5 what? Grams of water. Okay, and that will be your final answer. Okay, go ahead and flip over to the back of your paper. The last concept we're going to talk about today is something called empirical and molecular formulas. And I'm going to go through the difference between them, and then we'll do some examples on how to find them together. An empirical formula, often abbreviated EF, is a formula that tells you the simplest whole number ratio of atoms in a molecule. So it tells you the ratio of one element to another in a formula that occurs in nature. So for example, CH4 is telling us that the ratio of carbons to hydrogens when they bond in this way is always 1 carbon for every 4 hydrogens. Or another example would be 1 sodium to 1 sulfur to 4 oxygens. What you will notice about empirical formulas is they cannot be reduced any further. They are already in their simplest form. A molecular formula, on the other hand, tells you the actual or the exact number of each type of atom in a molecule. These can be reduced, okay? When we relate these to each other, you will see that the ratio of one element to another is still the same. We had 1 carbon for 4 hydrogens in an empirical formula. The molecular formula tells you how this compound is actually structured in nature with the exact number of each type of atom, but they keep the same ratio. It's still 2 carbons to 8 hydrogens, which would simplify down to 1 and 4. So the ratio is the same. Same thing here. Okay, so that's the definitions of those two words. What I would like you to do in this next section is to look at these formulas and tell me which one of these molecular formulas are also empirical formulas. So what I'm asking is which ones cannot be reduced any further. Go ahead and circle the ones that you think would be empirical formulas. You should circle these middle two. If you look at the subscripts, you cannot reduce PbO2 any further, and you cannot reduce MgCO2. These other ones can be reduced. So these middle two are labeled empirical formulas. Let's jump down to an example problem, like one you would see in your homework or on a test or a quiz. It says a compound has an empirical formula of PO3. If the molar mass is 158 grams, what is the molecular formula? Okay, so we know the empirical formula. We know the ratio of atoms is 1 phosphorus to 3 oxygens. But we want to know what the molecular or the actual formula of the compound is. The way that you will figure this out is you will do a ratio. You're going to take the mass of the molecular formula and compare it to the mass of the empirical formula. When you do this, you will get a whole number for your answer. Okay, so let's set this up. We know that the molecular formula has a mass of 158 grams. They told us that. So we're going to put 158 grams on the top for the mass of the molecular formula. What's the mass of the empirical formula? Well, they gave us the empirical formula. The mass would be found by going to your periodic table and adding up 1 phosphorus plus 3 oxygens. And I think you get 79 grams. So that goes here on the bottom. You're going to divide those, and you should get the whole number 2. This is telling you that the molecular formula weighs exactly double the empirical formula. So all you're going to do is you're going to take your empirical formula and you need to double it. And we would end up with P2O6 for the molecular formula. Okay, if you are one of the people that likes to check your work before you turn things in, you could always add up P2O6 and it should equal 158 grams if you did it correctly. Okay, this second example you're going to set up the same way. I'd like you to see how far you can get and then check back here to see if you got it correct. Okay, so in the problem they gave me the mass of the molecular formula at 354. I added up sodium, phosphorus, and 4 oxygens and got 118 grams for the mass of the empirical formula. I'm going to divide and I get the whole number 3. That means my molecular formula is exactly 3 times the empirical formula. Na3P3O12. And that's what we would end with.